Okay, good evening. So time flies. As we have posted an announcement, so next week, next Tuesday will be the final examination or final test. Okay, so today, tonight, we'll be finishing up all the lecture. Okay, so as I mentioned last time, I won't have time to cover all the materials that I originally planned for. So I will only focus on the most important parts. Okay. So I will quickly finish up this illustration of the dynamic barrier reconfiguration, which explains how 3G support packet switch data surfaces. And then I will go into the core network surfaces so that we will have an end-to-end understanding of the cellular network from the very low-level physical layer details all the way to the entire network, networking perspective. And I will hopefully will still have some time to talk about the examination, the format and the requirement and the scope. All right. So stay tuned. So let's quickly. And by the way, I've asked the TA to post assignment 2 as well. So she should have given you the corresponding deadline. Okay. So yeah, I'll talk about this after we finish the materials. Okay, so this is where we stopped last time. So remember, we were having a concept of a radial barrier. A radial barrier is a logical connection between UE and serving RNC. So it's just like a virtual connection, supported by the RLC. Okay, the RLC radial link control is to turn an unreliable logical channel into a reliable logical channel. All right, and but the concept of packet switch data surfaces is behind this connected radial barrier. You can have different types of transport channel behind to support this logical connection. Okay? Sometimes, if you have a small burst of data, you may support this logical connection using a common channel, something called common transport channel, such as the fetch in a downlink direction. And sometimes, when you have a big chunk of data to deliver, you still have an activated radial barrier. Okay? So from the application perspective, you are connected all the time. But then when you have a big chunk of data to transmit, the RRC, the manager, the supermarket store manager, will detect this demand, change of demand, and then basically coordinate the change from the common transport channel to the dedicated transport channel. Okay, so you can see that in this example, you can be connected or activated connection 24 hours. So to the user, the connection is totally the change of the transport channels or how you support the activated logical connection or how you support the radial barrier. This change is totally transparent to the user. The user at the logical channel level is not aware of this change underneath the logical channel. Okay, just like in the internet, you may have an activated TCP socket, right? And you can be connected to the server 24 hours. But what is behind this activated TCP socket is totally transparent to the user. Okay, same idea here. Okay, so last time we say that, okay, so since you have data plane and user plane, so when you want to connect when you want to establish a packet switch connection in 3G, there are two steps involved. The first step is to establish a connected control plane. The control plane of the UE has to be connected to the control plane of the serving RNC. So in particular, the RLC layer needs to be connected in both peers. So, and that's the first step. So the first step is initiated by the UE. Similar to the IS-95, how do you initiate a circuit switch connection? The user has to press the send button. So same here. The user has to initiate this packet switch connection by sending an RRC connection request. This connection request will go through the same random access procedure that we talk about, warm up the power, and then you wait for a random time before you retransmit. Exactly the same mechanism. Okay. The only difference is in that time you delivered a call origination request, and now you deliver an RRC connection request. That's the only difference. All right. And after you finish the step 1, as I mentioned last time, the signaling barrier, the logical connection for the control plane will be activated. Okay? Activated means there is a logical connection between the control plane of the UE and control plane of the serving RNC. Okay? And the one sitting on top of this signaling barrel is RRC, Radio Resource Control. All right? That would be the quote-unquote user behind this signaling barrel. So this is called signaling barrel because it's the barrel in the control plane. So this signaling barrel after step 1 will be supported using common transport channel in this example. All right? And then step 2 is to set up the connection on the data plane, so-called set up data barrel or set up a radio barrel on the control plane. And for that, it is initiated by the serving RNC to the UE. Okay? So in this example, after step 2, this will be an example of the multiplexing structure. Here, this is the signaling barrel, the logical connection for the control plane. This is the radio barrel for the data plane. So the user of this signaling barrel, as I said, is RRC. The user of this data barrel would be the, for example, TCP/IP. Okay, so that is for control plane. That's for this is for control plane. This is for user plane or data plane. And in this example, these two logical channel, activated logical channel, they are multiplexed into a common transport channel. Okay, so that's the function of the MAC layer to provide flexible multiplexing between logical channel and transport channels. Okay. Now, so this is the entire signaling procedure. So for step 2, it's initiated by the serving RNC. The RRC layer of the serving RNC will send this RB radio barrel setup message to the UE. And then UE, based on this setup message, will configure the MAC layer. Okay. For example, configure the MAC layer to do this multiplexing. Similarly, the serving RNC will also do the same configuration for the MAC layer. And then after the configuration is completed, UE reply with a radio barrel setup complete. So at this point, the protocol configuration will be like this. Okay? So both the UE and serving RNC will see a signaling barrel and a data barrel, both multiplexed into a common transport channel. And then the RRC state, the state of the manager, would be self-fetch state because no dedicated common channel, no dedicated transport channel was involved in this connection. Okay. Now, dynamic barrel reconfiguration is throughout the duration of your connected state. You may be connected to, in packet switch mode for 24 hours, but within this 24 hours, your demand comes and goes. That's the nature of the bursty traffic, right? So maybe you're doing video streaming on this packet switch connection. So sometimes the video burst will come and then you have a huge demand. That is like my supermarket analogy. Sometimes you have a huge influx of customer. And sometimes the supermarket is empty. Okay? So the RRC has to react and allocate appropriate resource in response to this change of traffic demand throughout your 24 hours connection. Okay? So there are 3 levels. So the trigger of this so-called dynamic barrel reconfiguration or dynamic barrel control is by change of traffic volume. Either there is an influx of customer into your supermarket or suddenly the supermarket is empty. Okay? So there are 2. So in response to this trigger, the RRC, the manager, can have 3 strategies in response of this change of traffic volume. The first strategy, the first method is to trigger a radio barrel reconfiguration. You try to reconfigure how the radio barrels are multiplexed into the transport channel. The second method or second strategy is to reconfigure the transport channel reconfiguration. The first strategy is to reconfigure the physical channel. Okay? The physical channel refers to the spreading cook channel that we talk about in CDMA. The signaling mechanism is very similar in these 3 methods. They are all initiated by the serving RNC. Remember, this reconfiguration is triggered by the RRC layer of the serving RNC. It's network initiated. It's never UE initiated. Okay? So, give you one example. So, in response to, let's see, so this is a decrease in traffic volume. So, think of the RRC as a supermarket manager. Suddenly, you see a decrease in the customers of your supermarket. When I say supermarket, that refers to the buffer, retransmission buffer in the RLC. Okay? So if you are the supermarket manager, now you see a reduction in the demand of the customers. Okay? But the customer is not yet empty. So in this case, what would you do? So this is the configuration before the change. Okay? So before the change, you see that this is the control plane, this is the user plane. So in this control plane, you have one signaling barrel, and the guy using this signaling barrel is the RRC layer. Okay? And this RB1, RB2 are the two data bearer, two logical channel supporting the data plane. So maybe you have multiple applications. Maybe one is a web browser, the other is a file transfer. I don't know, just as a random example. So this multiple application in the user plane will be using two radio bearer, okay, for their application flow. So now before the change of traffic demand, before the demand of traffic demand, the data plane RB1, RB2, and the signaling bearer, they are all supported by dedicated transport channel, DCH1, DCH2, DCH3. So these three logical channels in this level are supported by three dedicated transport channels. So it's a heavy engagement. So this is like in the supermarket analogy, you have three checkout counters for each of this virtual flow. Okay? And now after there is a decrease in traffic volume demand, the supermarket manager detected that, and then in this case, the connection is the same, okay? So the configuration of the logical channel is the same, because remember, all this change should be transparent to the application, to the users, right? So the web browser, the file transfer, and the RRC will still see an activated radio bearer in this interface. That is the same before and after. So this part doesn't see any changes. That is why I said this changes is transparent to the user. But what is changes in response to this decrease in traffic demand? Signaling bearer is still supported by DCH1, but then DCH3 is released, and then there is only DCH2, and data bearer RB1 and RB2 are now multiplexed into a single DCH2. Okay, so that is one example. So this is like in the supermarket, you have you close down one checkout counter. You only have two activated checkout counter. So one checkout counter is allocated for this signaling users. The other checkout counter is open to entertain the other two so-called data bearer virtual queue. So two virtual queue merge into one in one checkout counter, whereas the other signaling queue have its own checkout counter. Okay. So since before and after you still have common transport, you still have a dedicated transport channel. So the state of the supermarket manager, that is the RRC state, remains as sell DCH before and sell DCH after. Is that okay? So that's one example of the reconfiguration. In response to the decrease in traffic volume, the RRC manager can use this method, radio bearer reconfiguration. It changes how the radio bearers are multiplexed into the transport channels. Okay? A second example, in response to change of traffic demand, the RRC layer can also do a second layer, can also engage in what we call transport channel reconfiguration. So this is one example. Now, in response to a decrease of traffic demand, before the change, okay, so you have one signaling bearer and one data bearer in this case, okay. So both your control plane and user plane are connected, put it this way. And then before that, you have huge demand, right? So you have the signaling bearer is multiplexed into DCH1, dedicated transport channel 1. The radio bearer for the user plane is multiplexed into DCH2. Okay, so that was the configuration. But now since you have a huge decrease in traffic demand, so after the reconfiguration of transport channel, you can actually have signaling bearer and radio bearer both multiplexed into a common transport channel. So in response to this decrease in traffic demand, so the nature of the transport channel is changed. Okay, so therefore the state, RRC state, is from sell DCH to sell fetch. Okay, is that okay? And once again, this change is transparent to the user at this level. The user RRC layer and the user plane user application, they see the same interface before and after. Okay. And then once again, the signaling trigger is always initiated by the serving RNC by sending this transport channel reconfiguration. This is a control message sent by the RRC layer at the serving RNC, terminate to the RRC layer at the UE. Okay? And then in response to that, so UE receiving this would go through this change of the MAC layer configuration. And then after this change is completed, it will respond with a transport channel reconfiguration complete. So two-way handshaking to complete the reconfiguration. Now you need a complete response because you need to synchronize the mat state at the UE and the mat state at the serving RNC. The two-side mat layer needs to be configured in this way. Okay, so therefore they need to be synchronized. Is that okay? So that's the second example, transport channel reconfiguration. All right. Now, third example. Now you have an increase in traffic volume in this case, and then the RLC manager, the supermarket manager, can choose to use the most physical, can choose to trigger a physical layer reconfiguration, physical channel reconfiguration. Now, since this is reconfiguring the physical channel, so the signaling barrier, transport channel are not changed. Okay, so before and after, if you look at this protocol stack configuration, it's the same. What has been changed is the physical channel used to support these two transport channels are changed. So now you need a higher capacity. So what happens is the RLC layer at the serving RNC will issue a physical channel reconfiguration message. In this message, it will indicate the spreading factor needs to be reduced. Now, what do we mean by reducing the spreading factor? Remember, the spreading factor, as we talk about spectrum, is a parameter that determines how many broken pieces you chop a symbol into, right? So I always use 64 as an example because in IS95, the default spreading factor is 64. That is, you chop a symbol into 64 pieces, okay? So in 2G, you always assign a code channel to a user. The spreading factor is always 64. That is fixed. But in 3G, they use something called variable spreading factor. So the variable spreading factor works this way. So spreading factor is symbol duration divided by chip duration, right? So how many broken pieces I chop a symbol into? So that is given by this ratio, right? Now, if you write this into the bandwidth expression, so this is the transmission bandwidth. This is the transmission bandwidth divided by symbol rate, right? Because symbol rate is 1 over TS, transmission bandwidth is 1 over TC, right? Now, transmission bandwidth is fixed. For 3G, it's fixed to be 5 megahertz. So therefore, you see that the symbol rate is inversely proportional to the spreading factor. Can you see that? Because the bandwidth is a constant. So in 3G, when you allocate a code channel to a user, you are allowed to change the spreading factor. The spreading factor can range from 4 to 512. So if you want to allocate a code channel with a higher data rate, you should allocate a smaller spreading factor. On the other hand, if you allocate a code channel to a user with the highest spreading factor, 512, that means the data rate, the symbol rate for this user will be smaller, okay? Because of this relationship. So here, initially, you may be allocated a code channel with spreading factor, let's say 256. But since you now have a high demand, so if in this example, if you go through this physical channel reconfiguration, so the RLC may not change the signaling barrier, radio barrier, how they map to the transport channel, everything remains to be the same. But what they change is the spreading factor associated with the physical channel. So you can change to a lower spreading factor. In response to that, that means the physical channel used to support these two transport channels have a higher bit rate or higher symbol rate. And that's how you, so that is like in my analogy, this is like the minibus that come at once every 10 milliseconds. In 3G, a frame duration is 10 milliseconds. So that means every 10 milliseconds there is a bus, okay? So when you switch to a lower spreading factor, maybe the bus originally have 100 passenger seats. But if you reduce the spreading factor by half, that means you are able to double the symbol rate. So that means in the next minibus, after you change the lower spreading factor, the number of passenger seats will be doubled. Okay, that's how you try to react to this higher demand. Is that okay? So that is the physical channel reconfiguration. Once again, which strategy you adopt is vendor specific. So there are, again, innovation here behind the scene. So under what circumstances will you trigger which level of reconfiguration? This is up to different vendors' implementation. And there are lots of patterns behind this. Okay? And the standard only provides you these different mechanisms for you to reconfigure. But how do you choose to reconfigure at which level? This is, again, vendor-specific design. Is that okay? And all these triggers, they are initiated by the serving RNC. Okay? Keep this in mind. Is that okay? So hopefully this example will also help you to read the protocol stack diagram or understand the protocol stack. Okay? So what else? Okay, so we talk about closed-loop power control and also handover, so I'm not going to repeat it here. Okay? Any questions about packet switch data connection for 3G? And because of this mechanism, this enables you to be connected to the internet 24 hours without paying for 24 hours of airtime. Okay? You are no longer charged by how long you are connected. You are now charged by how much data you transmit throughout this period. So therefore, all the packages for 3G, 4G, 5G, for the packet switch connection, you are charged by packet volume instead of airtime. Okay? Because the fact that you are connected 24 hours doesn't mean you have to occupy dedicated resource for 24 hours. The resource used to support this activated connection changes dynamically, but this change is transparent to the user. The user will not be aware of this change. The user, for example, in this example, the two users in the data plane, web browser and file FTP, they will see the same activated connection throughout 24 hours. But below this RB1 and RB2, the transport channel used to support RB1 and RB2 may be reduced from 2 to 1, or maybe even switched to common transport channel. But these changes are transparent to the application on top of these logical connections. So that's the idea. Is that okay? And that's why through dynamic barrier control, the RRC can decouple the logical connection with the actual radio resource used to support the connection. This was tightly coupled together in 2G. In 2G, when you have a connection, a circuit is given to you, and the radio resource will be allocated to the circuit. Whether you use it or not is your own business. The network operator just start charging how long you have this circuit switch connection. But for packet switch connection, it's totally decoupled. You can be connected for 24 hours, but the radio resource allocated for this connection change from time to time. Okay? All right, so this topic about post-switch technology, I think I'm going to skip, okay? For various reasons. I think in other courses, you may have some exposure on MIMO, and also, if not, so in the next semester, I will be teaching one course for two lectures, and that will be also an opportunity for me to go over this as well. So I'm not going to repeat this, okay? So that would be for this radio access control, radio access interface. Any question? Radio access network, okay? Now, so we talk about the radio access network for 2G, circuit switch. Essentially, we talk about how you establish a circuit switch connection, and then power control, and then soft handover. That will be a very essential component behind any CDMA network. And then in 3G, which is also CDMA based, we focus on talking about how you establish a packet switch connection. Okay. And now, let's look at a higher level, even higher level, so-called core network, and the end-to-end application. Now, as we talk about in day one, the cellular network is actually pretty big. It's not just about mobile handset to the base station. That is only the radio interface. So in the previous part, part 2, we talk about the radio access network, which start from a base station controller or RNC, involving a number of base stations. And then each base station has its own radio interface to a number of mobiles. And that whole thing is called radio access network. But as you see in this protocol stack, for example, if you remember, there's a protocol stack diagram. Let's see. Here, maybe here. In this UE protocol stack, you look at, for example, the control plane. Serving RNC, SRNC, is not the end of the network. It's not the endpoint. There are, above this RRC, there are also other types of signaling messages or signaling protocols. So these signaling protocols terminate beyond serving RNC. So that means there are something else, something further than the serving RNC in the cellular network. So now we're going to explore these core network surfaces. Okay. So similarly, we will talk about both the circuit switch domain and the packet switch domain. So let's focus on circuit switch domain. So for the circuit switch domain, let's say GSM or IS95, beyond the base station controller, there will be, for example, mobile switching center. So again, if you remember, let's see, if you remember here, when we start talking about part 2, so this is the radio access interface. Beyond the radio access interface, this is the radio access network. Beyond the radio access network, we have mobile switching center, a bunch of mobile switching centers, right? So these mobile switching centers are the data path. That means your speech packet, if you're making a voice call, your speech packet, every single speech packet will go through base station controller and then terminate into mobile switching center, okay? So, and these entities are involved in delivering your user payload, so they are the data path. They are on your data path, put it this way, or user plane. There are two guys here, which we talk about, home location register, HLR, and visiting location register. These two guys are not involved in your user payload. Your speech packet do not go through these guys. So these guys are taking care of the control plane, okay, or control protocol. In particular, these two guys are the distributed database. This database keep track of where you are. The fact that you can engage in international roaming, the fact that the infrastructure know about where you are, is all due to this, okay? And these two guys collectively perform an important function called mobility management. Mobility management, MM. Now, again, if you ever pay attention to this protocol stack, MM, mobility management. Look at this protocol stack again. The MM is actually a control plane function, a control plane protocol, sitting on top of RRC. Okay, it's a control plane function above the RRC. So this MM stands for mobility management. This is the mobility management to keep track of where you are, okay, in the network for the circuit switch domain surface. And this GMM is the equivalent function, mobility management, to keep track of where you are for the packet switch domain surfaces. Now, why you have two separate stack of protocols for this? This is because initially, the evolution. So when they designed the core network originally for 2G system, the core network is the interface to the largest public network, right? For 2G surfaces, this is the core network for circuit switch surfaces. So your target public network that you want to connect to for voice surface at that time is PSTN, because PSTN is the largest public voice network. So that is what you want to interface. Now of course we haven't talked about this, but in some other courses, you may know PSTN is a bunch of switch, telecom switch, operating using circuit switch mechanism, right? So this guys is based on circuit switch. So if you want to connect or interface to this PSTN, naturally, this architecture should be circuit switch as well, so that they speak the same language, right? So in the data path, you speak PCM 64 kilobit per second. This is the dot wave format. On the control path, you speak this language called signaling system number 7, SS7. Okay, so in this way, both sides speak the same language, so the interfacing is easy. But then when you introduce 3G, where you have, in addition to voice, circuit switch voice, you also have packet switch data connection. And for the same reason, if this is a 3G network, for the packet switch domain, the packet switch domain target connection is the largest public network for the data application. So what is the largest public network for the data? Of course, internet, right? So you want to interface to internet. And internet speaks a different language than PSTN, right? So PSTN is circuit switch, internet is packet switch, and they speak IP. So for easy interfacing, you also want the core network for the packet switching to speak the same language. So it's IP based. Okay? So, and therefore, these are two natures of core network. So in the initial release 99, when they introduced 3G, to simplify the migration, they just keep two duplicated, two separate core network. We call this overlay approach. So they have a circuit switch core network and overlaid with a parallel packet switch core network. And because of that, they want to, the reason for that is this is simple. You don't need to, when you introduce a new packet switch surface, you don't touch or disturb the existing circuit switch surfaces. Okay, so that's why with this overlay approach, you see that this higher layer or core network control plane protocol, these are the existing 2G control plane protocols. So when you introduce the packet switch surfaces, you don't want to disturb this existing design, okay? Because the existing circuit switch core network is still there. So on top, when you want to introduce packet switch surfaces, you introduce a parallel layer for the packet switch. So in the protocol stack, you just duplicate another islands of control plane protocols for the packet switch network. So this side is for packet switch. This side is for circuit switch, okay? So you have these two things decoupled. So circuit switch and packet switch do not interfere with each other, put it this way. So therefore, for the mobility management, you have one layer talking about mobility management for circuit switch. And you also have a separate layer that talk about mobility management for the packet switch, okay? So these two are independent from each other. That means you may know about the location of a user from the from the mobility management layer, but you may not know about the location of the same user for the packet switch connection. This is because you can be located in the circuit switch surfaces to this base station, but at the same time, that means when you're located this way, that means you are ready to receive incoming call anytime, okay? And that's the circuit switch matter or circuit switch business. For the same mobile, the network may not know where you are. What does that mean? That means you may be disconnected from the packet switch surface at the same time, okay? So although you are known, your location is known to the circuit switch domain, your location will be unknown to the packet switch domain when you do not have a packet switch connection. That is, as we just talked about, when your radio barrier is disconnected. Okay, your RLC is the RLC idle state. In this case, from a packet switch domain, you are disconnected. So the network do not know where you are in the packet switch domain. At the same time, the network may know where you are in the circuit switch domain. Is that okay? That's the idea of this totally isolated islands of control plane protocol. Okay? Now let's focus on this mobility management. Now this boundary, as we talked about last time, is the boundary between, below this boundary, all these control plane functions will be taking care of radio-dependent functions. For example, out-of-the power control, soft handover, dynamic barrier control. These are radio-dependent functions, which are taken care by RLC. And above this line, those protocol control plane protocols are going to take care of radio-independent functions. Okay? So those functions are no longer related to the radio resource. I'll explain one by one. Okay? So let's focus on this mobility management here. Mobility management. So now there's one important concept, as I said. It's going to keep track of the location of mobiles in order to receive incoming calls. So this is for circuit switch surfaces. So this is for 2G network. Okay? And in 3G circuit switch domain, this is still applicable. Now, in order to keep track of the location of mobiles, it makes use of a distributed databases, home location register and visiting location registers. So these two guys are the distributed database. Distributed, meaning that the record of a mobile is split in these two databases. Home location register will maintain a permanent record for every mobile station. Okay? So, but then visiting location register maintain a dynamic record of the mobile station, okay, under its location area. Now, for a database, a black box model for databases, you have a record for every mobile. But in order to retrieve the record or to update a record, you need to supply with a key. Okay? Just like you go to the library, if you want to search a book, you need to supply with a key, with a certain ID. So same here, for the home location register, the key for a mobile record is called IMSI, International Mobile Subscriber ID. This is your SIM card ID, which is unique for every mobile. That means in the entire network, no two SIM cards will have the same ID. Okay? Now, so this is, as I said briefly, when we talk about part 2, this IMSI is sensitive. So you want to minimize the chance of transmitting IMSI over the radio interface. Because when a sniffer gets a copy of your IMSI, they can copy your SIM card. Okay? So anyway, so at the home location register, the IMSI is the key to retrieve or update the record, the permanent record of the mobile station. So the permanent record includes the address of the latest visiting location register, the MSC number. So these are the permanent record. Okay. Visiting location registers. There are many visiting location registers in a cellular network. Okay. Usually, a number of mobile switching centers will be associated with a certain visiting location register. Okay. So if you have 100 mobile switching centers in a network, you may have, 20 visiting location registers. So now, so it maintains a dynamic record of mobiles under its location area. So the key to retrieve the record or update the record at the visiting location register is no longer IMSI. It's called TMSI, Temporary Mobile Subscriber ID. So the corresponding record, so when you want to update or read the record for a user, you need, at the visiting location register, you need to apply a key called TMSI, Temporary Mobile Subscriber ID. Every visiting location register have its own TMSI database, TMSI resource. So when you know the TMSI of a mobile, the corresponding record for that mobile in the VLR consists of IMSI, that's the global ID, address of home location registers, and address of the mobile switching center. Also, location area ID. Now, I'll explain what do we mean by location area, okay, in a minute. Okay, so this is the background. I talk about location area. So every base station will have a location area ID. For example, this is location area 1, location area 1. Now, a few base stations can be clustered together to form a single location area. So that means the resolution of a location area could be bigger than the resolution of a base station. Okay, so in this example, let's say I cluster these two base stations to share location area 1, and then these two base stations to have a location area of 2. Okay? So the resolution of location area in my example is 2 base stations. Okay? So now remember when we talk about the call processing state in chapter 2, we say that mobile can be in idle state most of the time, right? When mobile is in idle state, there are 3 events that will trigger the mobile to leave the idle state and enter into active state. Which 3 events? The first one is call origination. User press the send button. That's the first. You want to make an outgoing call. That would be an event that will drive you to leave the idle state, enter into active state. That's the first event. Second event is you receive an incoming call request. That is page response. You receive a page message from the paging channel matching your mobile ID. That means there will be an incoming call request for you. That's the second event that will trigger you to leave the idle state. Okay? At that time, I briefly mentioned there is a third event. The third event is not related to call processing. The third event is actually location update. It's through this, so location update is part of the mobility management procedure. So this location update request is actually from the layer of the mobile station, sending this location update request to the layer in the mobile switching center, okay, in core network. Now, through this location update, it's only because of location update then the infrastructure will be able to know where you are up to the resolution of location area. So how does that work? When you are in a particular mobile base station, you listen to the broadcast, right, in the idle state. So some of this broadcast message in the paging channel will indicate what is my location area. So this base station, let's say in this room, it will periodically broadcast my location area is location area ID number 1. Okay, you blindfold yourself, you random walk, and so nothing happens. Okay, until if you drift, if you random walk into another location area. So you blindfold yourself, random walk, and suddenly you hear a broadcast in a room saying that my location area is 2. And then you compare this 2 with your local location area. Your local location area is only 1, right? If you hear a broadcast that the location area is different from your local location area, then you know you move to another new location area, right? In this case, you need to report this location, or you need to update your location to the infrastructure. Therefore, you will leave the idle state, and then you will assemble a location update request to tell the infrastructure, my latest location area is number 2. Is that okay? So this is event trigger. As soon as you hear from the base station broadcast that the current location area is different from your local copy, then you do a location update request. Is that okay? So the mobile needs to proactively tell the infrastructure the latest location area. In this way, the infrastructure will be able to keep track of where you are, but only up to the resolution of location area. That means if you cluster 2 base stations together to share 1 location area, then the infrastructure will only know where you are up to the resolution of location area. Okay? If you cluster 3 base stations together for 1 location area, then the infrastructure will know where you are up to a resolution of this location area, which is 3 base stations. Is that okay? Now, another very important concept here that I was surprised to see that some of these field engineers with 5 years experience even confused with this question that I'm going to talk about. Now we talk about mobility management. The name may be confusing by itself, okay? But remember in the previous chapter when we talk about CDMA system, we also talk about handover, right? Remember soft handover, right? As the mobile move between base stations, when mobile has to, from time to time, measure the pilot strength, right? To keep track of, to catch the handover opportunity, whether it's an add event, drop event, or swap event, right? And report this to the base station controller for handover. So wouldn't that, so now we're talking about mobility management. So what's the difference between handover and mobility management here? Understand what I mean? What's the difference between the handover mechanism we talked about in previous chapter and mobility management here in this chapter? Both are referring to mobility control, right? Or mobility management. What's the difference? Now, if you go to interview for Huawei or China Mobile, this could be an interview questions. What's the difference? What's the difference between handover procedure we talk about in part 2 and the mobility management location update mechanism here in this chapter? The very important difference is when we talk about handover, the prerequisite is the mobile is in a conversational state. The mobile has a dedicated traffic channel associated with that. So handover is to maintain the traffic channel handover seamlessly with respect to the user, right? Here, mobility management is we're talking about when mobile is in idle state. The mobile doesn't have a dedicated traffic channel yet. The whole purpose of mobility management, the why the infrastructure has to keep track of where you are, it's not just for fun. It's to prepare the infrastructure to support call termination, okay, effectively, as we'll talk about in a minute. Okay, so keep this in mind. mobility management here is not the same, very different from handover that we talked about before. Handover is a layer 1 mobility, if you can think of it this way. It's a layer 1 mobility talking about when you only need to worry about handover when you have a traffic channel associated with you, okay, allocated for you. It's a layer 1 mobility. Here, this is talking about mobility management when you're in idle state to prepare you for receiving any incoming call request at any time. Okay, so that's before you have a traffic conversation state, before you are allocated a dedicated transport channel. Before you're allocated a dedicated traffic channel. Is that okay? Now keep this in mind. Okay, so now let's look at how it is done, mobility management. Okay. Now the location update request, now from the mobile perspective, it's very simple, right? Every time you hear a new location area broadcast, you just go and trigger, get into the access state, and then you go through the same access procedure. Except that the message you want to send in the access procedure is now location update request. Okay? And after you send it successfully, you go back to the idle state. That's the only difference. Now, from a mobile perspective, it's very simple. But from the infrastructure perspective, there are 3 different cases. Let's look at a simple case, inter-location area movement. So this is given by this network architecture like this. Suppose this is the original location area 1, and now you move to location area 2. And these 2 base station clusters are connected to the same mobile switching center. And therefore, they are connected to the same visiting location register and the same home location register. Okay? So when mobile detects this change in location area, so it will initiate a location update request, right? So that's simple. This location update request is originated from the MM layer in the mobile station, terminate to the MM layer at the mobile switching center. Okay? So now the mobile switching center, so this location update request message will include the previous location area, LA1, in this for example, the previous mobile switching center address, the previous visiting location register address, and the TMSI, temporary mobile subscriber ID. Okay? Now, in case this is the first registration, in case this is the first time the mobile registers itself to the network, then it will send IMSI instead of TMSI. Okay? So, but let's say this is a steady state. So, mobile will identify itself in the visiting location register through the key TMSI. So now, step 2 is now mobile switching center receiving this location update request. What to do next? Okay? Since there's a change in location area, so that means the mobile switching center needs to update the database's record to reflect the latest location, right? So now, first of all, mobile switching center has to go through a database transaction. So this database transaction is a signaling transaction. So it's actually based on SS7. I erased that picture. So it's based on SS7. It's a language. Okay, it's a control language for circuit switch network, similar to PSTN. So this is a database transaction. So database transaction always for example, if you go through database query, you supply with a key, the database responds with the record. If you go with database transaction like update, you supply with a key and the new data. Then the database, based on your key, identify the record and then update the record. Okay, so database query and database update, two important transactions. So in this case, this mobile switching center will have to initiate a database update, right? Because the location area has been changed from LA1 to LA2, right? So mobile switching center will issue a database update transaction to the visiting location register. Remember, in this example, the new location area and the old location area all connected to the same mobile switching center, and so therefore they are served by the same visiting location register. Okay, so the database is the same before and after. So step 2, mobile switching center will issue a database transaction. Step number 2 is a database update transaction. So the mobile record is here, before and after the change. Mobile record is always here. So in the update, in the update record, mobile switching center will supply with the TMSI. The TMSI is as a key, database key to identify the record for this mobile, right? And then mobile switching center will also supply with the MSC address, TMSI, previous LAI, and target LAI. Okay? Based on this information, mobile switching center will be able to update the record for this mobile. Basically, that means in step 2, the mobile record will be updated from LA1 to LA2. The other records remains unchanged. Is that okay? Now, visiting location register, after completing this database update, it also needs to consider, is the update completed? Okay, what do we mean? Because the mobile record is split between home location register and visiting location register, right? So if you are the visiting location register, yeah, you update your local record, LA1 to LA2. But you also need to consider, do I need to update the corresponding record in the home location register or not? Now in this case, fortunately, the visiting location register, notice that LA2 and LA1 belongs to the same mobile switching center. So it doesn't need to update the mobile switching center address. It just needs to update the location area record, which is local in the visiting location register. And this update will be completed in this case, because you don't need to update the record in the home location register in this case. All right? So therefore, it will reply and add to the mobile switching center, meaning that the database transaction is completed. Now, to the mobile switching center just issue a database update, okay, to the visiting location register. Every database transaction comes with an ACK. It's a two-way handshaking. So if I'm mobile switching center, I just give you a database transaction update request. Then you, as the visiting location register, you need to determine how deep you need to update into the databases, right? So in this example, fortunately, the update is just local to the visiting location register. After you finish an update, you send me back an ACK. Then I know my database transaction is completed. The update is completed, okay? So therefore, step 3 is to reply and add to the mobile switching center, completing the database transaction here, okay? So after step 3, mobile switching center realize my database update is completed, okay? And they will acknowledge the mobile. Step 4 is basically acknowledging the mobile, completing the location update procedure. Is that okay? So through this update, in this easy case, the infrastructure, in particular, the visiting location register, will know the latest location area of the mobile, being location area 2, okay? Now, but this is not always, we are not always that lucky. There is a second case. The second case is inter-mobile switching center movement. That is, it could happen that the new location area corresponding to the base station that are connected to a different mobile switching center, okay? Now, if they are connected to the two mobile switching center, let's say in this case 2, let's say these two mobile switching centers are served by a common visiting location register, okay? Now in this case, the mobile is totally unaware of whether you're talking about case 1 or case 2. In whatever case, the mobile just initiate a location update whenever you see a new broadcast location area ID from the base station. The difference, so step 1 is the same. Step 1, the mobile will send a location update request and also supply with the TMSI as a key and then new location area, etc. Okay, so this message is the same in step 1 in all cases. The difference is now the mobile switching center receiving this location update request, it will be the same to issue a database transaction, okay? Database transaction to update the record to the visiting location register, okay? So step 2 is also the same as before. So mobile switching center issue a database update to the visiting location register. Now, the visiting location register has to consider, in this case, how deep it needs to update the record. Now, in this case, visiting location register, notice that LA1 and LA2 belongs to 2 different MSC. So that means you need to update both the location area ID and the MSC addresses, okay? Now, location area ID is in the visiting location register record, but MSC address is a record in the home location register. So that means this time, I'm the mobile switching center, you are the visiting location register. I give you a database update transaction request. You locally have to decide, okay, I need to update my location area record locally. But at the same time, I also need to update the home location register record for the mobile switching center address. So in this case, you, the visiting location register, has to go through the update into home location register, right? As I said, the records for the mobile in home location register, the key for the records are IMSI, your SIM card ID. So how do you know? You are the visiting location registrar. You need to update the home location register record. So that means you need to supply with the key IMSI. How do you know the IMSI of the mobile? The IMSI of the mobile is actually in the home location register record, in the visiting location register record. Okay? So once you retrieve the record using TMSI in the visiting location register, the record will contain IMSI. And then you can use this as the key for retrieving the record in the home location register. Okay? So now, after, this is case 2. After step 2, the visiting location register update the location area ID locally. At the same time, obtain the IMSI from the visiting location register record. And then VLR will issue another database transaction to update the record in the home location register. Okay? Now, home location register receiving this update request will just retrieve the mobile record from the IMSI and update the MSC number. After home location register finish the update, it will reply with an ACK to the visiting location register so that the VLR know that the database transaction between 3 and 4 are completed. Only until then the visiting location register can give me an ACK. Step 5 is you give me back an ACK. So therefore, the action, how deep you need to update the databases, is transparent to the mobile switching center. If I'm the mobile switching center, I just give you one database update request to the visiting location register. You determine on your own. You don't need to tell me. You determine on your own how deep you need to update into the databases. But as long as you make sure that all the concerned records are updated, you give me back an ACK so that I know my request is completed. Is that okay? So this design also makes sure that, enable the mobile switching center doesn't need to worry about how deep it needs to update. It's all the duty of the visiting location register. You will determine how deep you need to update. Okay? And then after that, the mobile switching center, realizing that the location update database update is completed, then you will send back an ACK to the mobile, completing the location update request. Is that okay? Again, mobile does not need to be, so whether this is case 1 or case 2 is totally transparent to the mobile. Mobile just trigger a location update request in all cases. Okay? Now, but case 2 is not the worst. Case 3, it will involve inter-visiting location register movement. So what does that mean? It could happen that the new location area 2, corresponds to base station connecting to a different mobile switching center, and this different mobile switching center also served by a different visiting location register. Now this is more complicated than case 2. Now why do I say that? In this case, because now when mobile on this new location area, again, send a location update request, step 1 is the same. Mobile send a location update request to the mobile switching center 2. Mobile switching center, using the same practice, it has to issue a database transaction to update this record at the connected visiting location register. But in this case, this visiting location register 2 doesn't have the mobile's record because the mobile's record was in VLR1, right? So when you have when VLR2 receive a database transaction request from the mobile switching center, the VLR2 does not have a record for the mobile station. So in this case, VLR2 will consult the previous VLR for this mobile to retrieve the record. Now, again, for step 2, for VLR2 to retrieve the record, it needs to supply with the TMSI. So TMSI is actually in the location update request. Okay, so VLR2 will forward this request to VLR1, supply with TMSI. So VLR1 will be able to retrieve the record and then transfer the record to VLR2. After step 3, VLR2, the new VLR, will be able to create a new record for the mobile. Okay? Now, but this is not done yet because now this involves updating the home location register as well. Okay? So now the VLR2, after creating a local record, a new record for this mobile, it will decide, okay, I need to update the home location register as well. So it will issue another database transaction request to the home location register, updating the record of the mobile switching center address and also the VLR address. Okay. Now, after at the home location register, after it updates the local record, it also needs to think, okay, in this case, do I need to stop, is the update completed, or do I need to go through some additional procedure? And it turns out it also needs to go through additional procedure. Step 7, because now the mobile record exists in 2 visiting location register. So this is a duplication of record. This is an outdated record. So the home location register needs to delete the record, okay, to make sure that the old record is deleted. So the visiting location register 2 will have the updated record. So home location register will issue another database transaction to delete the record. After this delete of the record is completed, only until then home location register can reply with an ACK. And only until then, the visiting location register 2, VLR2, can reply with an ACK to the mobile switching center. So in this case 3, if I'm the mobile switching center, I issue a database update request to the visiting location register 2. I need to wait for some more longer time before I can hear the acknowledgement from the VLR2, because behind the scene, you need to go through various procedures to retrieve the record, create new record, update home location register, and also delete the obsolete record. Okay, so and when mobile switching center receives an ACK, it will also reply with an ACK to the mobile, completing the location update request. Is that okay? So this is the location update, so-called mobility management procedure. Is that clear? Okay. So once again, if you just look at the mobile side, the mobile side is very simple. Mobile side just need to send a location update request whenever you hear a new location area in the idle state. Once again, okay. It's the infrastructure that determines how deep you need to update the databases. Okay. Now, why you need mobility management? As I said, with mobility management, the infrastructure will be able to tell where you are, right? Up to the resolution of a certain location area. But so what? Why? Why do the infrastructure need to know where you are to start with? Okay? So this has to go with call processing. Now, with call processing, there are 2 call processing. One is call origination, right? User press the send button. Now, for user press the send button, the infrastructure does not need to know where you are, because the initiation is from the mobile. Okay, so when you press the send button, in the previous chapter, we talked about the call processing procedure, right? The mobile has to send call origination requests, go through the access probes, eventually reach the base station, right? But that was a simplified picture. In fact, the through handshaking is not the base station that handles your call request. It's actually the call origination request is coming from a protocol layer in the control plane called CC, call control. You see that CC is riding on top of mobility management. So call control is actually utilizing the location service provided by mobility management. Okay? So the call origination request is originated from CC at the mobile and terminates into the CC layer at the mobile switching center. It's not at the base station. Okay? So this is a full picture. So mobile press the send button, send a call origination request over the radio interface to the base station, but base station do not look at that. Base station will just forward this call origination request to the base station controller. Base station controller will not look at that. Base station controller will forward to the mobile switching center. It's the CC layer at the mobile switching center that will look at this message and process it. Okay? And then step 2 is the mobile switching center. Then what do you do? Suppose you want to make a phone call to your to your office number, fixed line number. The mobile switching center will have to consult the home location register, consult the visiting location register. This is issue a database transaction to query the record for this mobile. So you need to check the visiting location register, whether there is a record for you, whether you have paid your bill, etc. Right? Are you allowed to make a phone call in this network? Suppose the visiting location register forward with a positive reply, the mobile switching center will go ahead and set up the data trunk to the PSTN, to the office number. Okay, and after that you will be able to make a call. Okay, using a standard procedure. Now in this entire procedure, you see that because the call is originated or initiated by the mobile, the infrastructure just does not need to know where you are. And this outgoing call request can still be supported without problem. So the mobility management is actually not for call origination. The mobility management is for call termination. Okay. Now with call termination, let's say an office number, a fixed line number, call your mobile. Call your mobile. So why the infrastructure will need to know where you are? So this is the office number. Let's say I call your mobile. Okay. Your mobile belongs to a certain operator. So this number, okay, will go through the PSTN, and the PSTN examining the first few digits of your number, we realize that this number belongs to operator D. Okay. Then it will set up a trunk to the operator D, to the gateway mobile switching center of operator D, mobile operator D. Okay. Now at this point, there is a call request for this mobile 1, 2, 3, 4, 5, 6, 7, 8. Let's say this is the number I want to call. So this call request at the gateway mobile switching center. Now you are the gateway mobile switching center. What can you do with this call request? Somebody is looking for this number 1, 2, 3, 4, 5, 6, 7, 8. Now if you do not know where is this mobile number 1, 2, 3, 4, 5, 6, 7, 8, then how do you find this number? Let's say you are the security office in this campus. Let's say someone come into the security office, I want to look for this particular student. You know that this student is in the campus, but you don't know where he or she is. What can you do? If you really want to entertain this call, what do you need? You need to have a broadcast for the entire campus. This particular guy, please come to the security office, right? You need to broadcast throughout the entire campus. Same here. If the infrastructure does not know your location, in order to support this incoming call, the infrastructure needs to trigger every single base station. And we are talking about 10,000 base stations in a network, typical small network in Hong Kong, 10,000 base stations. You need to trigger this 10,000 base station to send paging channel message to look for this particular mobile, 1, 2, 3, 4, 5, 6, 7, 8. Okay? And hopefully, wherever you are, you will receive one of these page message, and then you will go through page response. Right? That would be the procedure to do it. But if every single incoming call require the entire 10,000 base stations to send a page message, you can see that the paging overhead will be very large, right? So that's not the way to do. Now, on the other hand, if you know where is this mobile, up to the location area, let's say in my example, a location area cluster consists of 2 base stations, and you know that this guy is in location area 1, then what can you do? Just like my campus example, right? Some stranger come to the security office, look for this guy, and somehow the security office know about where each one of you are, up to a certain resolution of a classroom. And then very, very easily, right? The security office just needs to broadcast in this room, whoever, go to the security office, right? Same here. If the infrastructure know about where you are, know that you are in location area 1, then you just need to inform this 2 base station in location area 1 to send page message for you, right? And then when you receive this page message, you will go through a page response and set up the call, answering this incoming call. Is that okay? So that's why, in order to support efficient call termination, you need mobility management. Okay, so that's why mobility management is providing a location services to make the incoming call control easier. Okay, so therefore the procedure will be when gateway mobile switching center, this is like the security office in this campus, receiving such an incoming call request for a particular mobile. This guy will first consult the home location register. The home location register will consult the visiting location register and retrieve the record. From this record, it will know about the mobile switching center addresses. Okay, so it will set up a trunk to the target mobile switching center and also ask the corresponding base station in the location area to send a page message for this mobile. Is that okay? So that would be basically the idea, why you need mobility management. Now, here comes the question. So as an operator, you have the flexibility to determine how big is a location area cluster size. So what would be the consideration? Would you prefer a very large location area cluster? If you have a large location area cluster, let's say one location area cluster consists of 10 base stations instead of 2. So in this way, what is good or bad about this? If you have a very big location area cluster, one location area consists of 10 base stations, then is it good or bad? One location area cluster consists of 10 base stations instead of 2. Is it good or bad? Now, if one location area cluster consists of 10 base stations, then every time there is an incoming call for a mobile, how many base stations you need to send page message? You need to have 10 base stations sending page message, right? So in this way, is it good or bad? This is bad, right? Because the downlink paging overhead to support one call termination would be higher, right? Correct? So from that angle, you would prefer, it seems that you prefer a smaller cluster, right? Now let's go to the extreme. If now one location area cluster consists of one base station only, is it good or bad? That means in this case, every time there's an incoming call request for a particular mobile, I just need to ask one base station to send page message, right? So that means the downlink paging overhead will be substantially reduced, right? So this is good, right? Agree? But in this case, then why don't we just have one location area per base station? One base station per location area. But sometimes we prefer multiple base stations per location area. Why? What's wrong with only having one base station per location area in this case? The downlink paging overhead is very low, right? But if you do it this way, the uplink location update overhead will be very large, right? Because when you random walk, every time you see a new location area, you need to do location update. Can you see that? So that is a intimate trade-off between location update request overhead. This is an overhead, right? This is an uplink overhead versus downlink paging overhead. So there are trade-off between these two, and the trade-off is realized by designing the location area cluster. So the optimal cluster size is determined by the frequency of incoming call requests for a network. Okay, so if this particular mobile network has very frequent incoming call requests for some reason, people like to call the mobile number of these customers for this mobile network. If that's the case, then would you prefer larger cluster or smaller cluster? Of course, you prefer smaller cluster, right? Because now you have frequent incoming call, and you want to reduce the downlink paging overhead associated with this incoming call, right? So in this case, you prefer to use a smaller cluster. On the other hand, if the incoming call request statistics is very sparse, only once in a while you have an incoming call request, then in that case, the sweet spot becomes you prefer a larger cluster size, right? Because you want to reduce the location update overhead in the uplink. Is that okay? So the optimal size depends on your incoming call request statistics. Is that okay? So different operator may have a different cluster size, depends on its own incoming call request statistics. Okay. Now, another remark. When I talk about this protocol stack, I said that this is for circuit switch domain, right? Which is what we are talking about now. This is for packet switch domain. Now, I mentioned that for the mobility management, they are independent protocols, right? So that means in the circuit switch domain, through the location update procedure, the infrastructure will know about where you are up to the resolution of a location area, right? For the GMM, this is the packet switch domain counterpart of mobility management. They have a similar procedure, but they do not use the location area. They use something called routing area. So each base station, in addition to location area ID, they also have routing area ID. The routing area cluster can be different from location area cluster. That means a location area cluster may consist of 2 base stations, but routing area cluster may consist of 3 base stations because these 2 domains operate independent from each other. Okay? So why we have this independent arrangement, I have explained, because they take an overlay approach in the core network design. So they don't want to touch whatever is there in the 2G. They just want to overlay something new for the 3G packet switch. Okay? So that's why they operate independently. And it also makes sense because, as I said, right, why you don't use the same cluster size between location area and routing area? That's because, as I said, right, the optimal cluster size is determined by the statistics of incoming call requests, right? So an operator, a 3G operator, may have a different statistics of incoming call. It may have a high probability of incoming call for circuit switch services, but low probability of incoming packet call. I mean, when I say incoming packet call, that means if this is a packet switch, the internet may have a incoming IP address, an incoming IP packet with the IP address belonging to some of the mobile, right? So it may have a high statistics for incoming IP packet, but low statistics for the circuit switch incoming call. The two statistics of the circuit switch domain and packet switch domain can be different. And because of that, you will require a different clustering strategy for the packet switch domain and the circuit switch domain. Is that okay? And because of that, so you can be, the infrastructure can know about where you are in the circuit switch domain. I know you are in location area 1, okay, for example. But at the same time, I may not know about where you are in the routing area. Because if, let's say, you are not connected in the packet switch domain, then the GMM layer will have no idea where you are. Is that okay? So the key is the packet switch domain and circuit switch domain are completely isolated in the overlay approach. Is that okay? Now, one final remark for illustrating this importance is, okay, so this reminded me of a kind of old movie, again, to your age. It's around year 2000, around that time. It's a mainland movie. It's called, I'm not sure if you heard about that or watched this movie or not. It's called 手機. Heard about this movie? Okay, anyway, it's kind of a funny movie, supposedly. So the story is like, so it was about a middle-aged man who has a wife who married, right? And then, but he also very active, and he kept a lot of mistress at the same time. So he found it very troublesome to explain to his wife when he was with the mistress, right? So when the wife called, it's very inconvenient, and it's also very annoying to always have to find excuse to explain to the wife why he cannot pick up the call. So, and then at that time, the mobile is not like today's smartphone. At that time, the mobile is had the battery separable. Those Nokia phone, if you have an idea. So the trick that in the movie, the guy has a trick. So the trick is, if you want to not being able to call by his wife, the way is not to switch off your mobile. If you switch off the mobile, it's different from you take away the battery. Okay, so in the movie, the guy will just take away the battery, and that will safeguard himself from the problems. Now, what's the difference? Now, if you switch off, power off the mobile, when you power off the mobile, you will go for a deregistration procedure before you really power off. So in the deregistration, your databases, home location register and visiting location register will know that you switch off your mobile. So when your wife calls you, okay, at the Gateway Mobile Switching Center, you go through database query and transaction. The information retrieved from the databases will indicate you have switched off your mobile. And then the network will, because you have switched off your mobile, right? So there's no way for the network to go through page message to look for you. So the Gateway Mobile Switching Center will then play a voice recording saying that the mobile you're trying to call has switched off your mobile, switched off the mobile. So please call again later. Okay, so this kind of voice recording. On the other hand, if you take away the battery, take off the battery, what's the difference? If you take away the battery like this, there is no way that there will be a deregistration procedure. So the database entry will still indicate you are in location area 1, right? So when your wife calls you at the Gateway Mobile Switching Center after database query, it will respond with a location area 1, okay? So then the call will proceed to the target mobile switching center, and you will ask the base station in location area 1 to send page message. But of course, since you take away your battery, you won't be able to do a page response. So after timeout, then the Gateway Mobile Instruction Center will play another voice recording saying that the number you have called cannot be reached. Please try again later. So you see these are two different situations, right? In the first case, the guy has to explain to his wife why you switch off your mobile, right? What's wrong with you? In the second case, the guy can easily say that I have no idea. I'm in a dark coverage. I'm in coverage hole. I don't know. I cannot receive your call, right? So that makes some differences. So basically, this is to hopefully give you an end-to-end picture of how call termination is done. All right. Now, of course, nowadays with smartphone, you won't be able to take away your battery in the same way as before. Okay. So if you power off your mobile, you know that you have to be mindful that the one calling your mobile being switched off will receive a voice recording saying that your mobile is switched off. Okay. Now, one final topic regarding this is an extension of this mobile call termination is the topic of international roaming. Now, starting from 2G onwards, so for example, GSM. GSM has a broad coverage in the world, right? So everywhere, even in the US, you have GSM coverage. So if you travel, if you are a GSM user, let's say from Taiwan, and you travel to some other country which also have GSM coverage, you are able to have international roaming. That means you will still be able to make call and receive call, okay? But there are three scenarios associated with international roaming. Scenario one is when a person in Taiwan, so the home network is in Taiwan, I'm sorry, let me try again. Let's say the user is John. John is the home network. The mobile network is in Taiwan. Now John traveled to Singapore, okay, on business trip. Now a person in Taiwan called John, okay? In this case, now this person in Taiwan called John's number. John's number is the Taiwan number. So to this guy, it doesn't know I'm calling an international call. I'm making an international call because I'm just calling a regular Taiwan mobile phone number. And this will result in a local call and an international call because now physically, John is in Singapore, right? So if John answers the phone, then usually the caller is charged with a local GSM call. And that's fair because to the caller, I'm just calling a Taiwan number. I thought I'm making a local call, right? But then John is aware that he is in Singapore. So if he chose to answer the call, then John will be charged for an international call from Taiwan to Singapore. And this arrangement is fair, right? Okay? So that's not an issue. Scenario two, let's say a person in Hong Kong, okay, call John's number, which is a Taiwan mobile number. Now in this case, the caller will be mindful, will be aware that I'm making a Taiwan international call, right? So, but John is in Singapore, so therefore the connection will involve in two international calls. And then the split of the charge will be usually the caller from Hong Kong will be charged with Hong Kong to Taiwan international call. And that's fair because when the caller makes the call, you know you're calling a Taiwan number, right? So you are prepared to pay for that international call. And John, if he chose to answer the call, it's also fair because now John will be charged with Taiwan to Singapore segment, okay? So this two arrangement is fair. It's not a problem. Now the troublesome scenario is scenario number three. Let's say a person in Singapore called John's number. Now in a naive way, if you do not do anything about this, due to the constraint of SS7, which I'm going to explain, a person in Singapore called John's number, Taiwan number, in this call will result in two unnecessary international segments. So from Singapore to Taiwan and from Taiwan back to Singapore, okay? Now, in this case, obviously, this arrangement is highly suboptimal because both caller and the caller party are both in Singapore. So the question is, can this unnecessary international call be avoided? Okay, and this is called time bombing effect. So let's look at, before we talk about the solution to scenario 3, let's look at why we have this time bombing effect to start with. This is due to the restriction of SS7. So SS7 is designed for PSTN, signaling language. And for PSTN, it's not supposed to be mobile. But then when you use SS7 as a signaling language to a mobile network, then you will have this kind of constraint. So let's look at what happened to scenario 3. Now, suppose, let's say this is Jenny. Jenny in Singapore. John is also in Singapore. Okay. Now, Jenny called John's mobile number, which is a Taiwan mobile number, okay, to the local PSTN in Singapore. The local PSTN examine the number, examine the country code, will realize this is an international call belonging to Taiwan. So this call will be routed to an international switching center in Singapore. Any international call will be routed to an international switching center. Now, let you be aware, in those days, even today would be slightly better, but in those days, in the 90s, there are two types of local operator in PSTN. This is called local telephone operator. This is called international carrier. These are usually two different companies. Okay? Give you some example. In Hong Kong, in Hong Kong, it's called Cable and Wireless and Hong Kong Telecom. These are the two. One is a local operator, the other is an international carrier. In the US, it's called regional bell telephony and AT&T. So AT&T is was an international carrier in the US. Okay? So these are two different companies, two different carriers. As long as the local PSTN detect this as an international number, the call will be routed to the international carrier. Now, international carrier examine the country code. This is the Taiwan's country code. It will then set up the trunk to the international carrier in Taiwan. Okay. Once Taiwan receives this incoming call request, it will look at the local number. It belongs to a mobile operator, okay, operator D in Taiwan. So the call will be set up to operator D, GMSC, the Gateway Mobile Switching Center in operator D in Taiwan. Now, at this point, this is following the standard incoming call procedure. This Gateway Mobile Switching Center will consult the home location register, and home location register will consult the visiting location register, which is in Singapore, doing this database transaction. So after this database query, in step 5, the Gateway Mobile Switching Center will realize, okay, John is in Singapore. So it will continue to set up the trunk all the way from Taiwan back to Singapore to the Mobile Switching Center G, okay, and then inform the base station concerned in the location area to page for John. And let's say John answer with the page response. Eventually, the end-to-end data path will be from here to here. Okay, so that's why, although both the caller and the caller party are both in Singapore, this kind of standard arrangement will result in two international segments. Okay, now I mentioned that this is a constraint. You may wonder, okay, in this signaling procedure, by the time that Gateway Mobile Switching Center in step 5 realize the called number is actually in Singapore. By the way, by the time that after step 5, this guy will know, right? But this is already too late because in SS7, signaling system number 7, it can only go forward. When you set up a trunk, it can only go forward. Once you set up a trunk, you cannot release the trunk. Okay? So at step 5, by the time that you realize the called number is actually in Singapore, all this trunk has been set up. Okay? So therefore, there is no way for you to release the trunk and set it up again. That's the restriction of the signaling system number 7, because that was designed for PSTN, and PSTN doesn't have this kind of issue. Okay? So, and therefore, whenever you set up a trunk, you can only go forward with the SS7. So the only thing you can do at this point is to continue to set up the trunk back to Singapore and then to the destination. That's why you have this unnecessary international segment from Singapore to Taiwan and from Taiwan back to Singapore. Okay? So if you want to improve this situation or eliminate this kind of unnecessary international call, you need to do something. You need to change this standard signaling procedure. Now, there are several solutions. The first solution is called roamer location cache. Now, with roamer location cache, it's like this. When John, okay, travel to Singapore, when you first power up the mobile, it has to go through registration, the standard location request, right? So the location request will basically, John will make a location update, and then Mobile Switching Center in Singapore's network will create an entry in the visiting location register, as we talk about in the mobility management, right? And then visiting location register will update the record to the home location register in Taiwan, right? Now, the roamer location cache is in this solution 1 is installed at the International Switching Center in Singapore. When visiting location register try to update the record for the home location register, this roamer location cache will try to sniff the copy and create a local copy. In other words, this roamer location cache acts as a proxy for the home location register for John. It's like a proxy. Okay. Now, this is the situation in the registration. So after registration, the dynamic record exists in Singapore's visiting location register. The permanent record exists in two places, in roamer location cache in Singapore and also the home location register in Taiwan. Now, when Jenny make a call to this John, okay? Now, the call in the same way is a Taiwan Taiwan international number. So the Taiwan number is routed to the international carrier in Singapore network. Now, the international carrier, in this case, has to deviate from the standard SS7 procedure. Instead of setting up the trunk to the Taiwan network as before, it can first query the roamer location cache to see if this call number is a potential roamer. Now, since this guy keeps the same record as home location register in Taiwan, so you will find a record for this mobile, and then you will respond to the international switching carrier, and then find that this call number, John, is actually a roamer in Singapore. So instead of setting up a trunk to the Taiwan ISC, this guy will set up a trunk directly to the mobile switching center of the Singapore's mobile network. And then in this way, you will proceed the call, avoiding unnecessary international segments, right? Remember, this is still subject to the constraint of SS7. The SS7 constraint is once you set up the trunk like this, once set up the trunk forward, you cannot go backward. So the only way for you to avoid this is to avoid setting up the trunk to the international switching carrier in Taiwan. Okay? So in solution 1, the stopping point is at the international switching carrier, switching center in Singapore. Okay? So in this way, you avoid unnecessary international segment. Well, you may wonder as an operator why I want to avoid unnecessary international segments in a roaming call. If you use a standard procedure like this, the operator will be able to charge higher, right? Will be able to charge, even in this scenario number 3, the operator will be able to charge international segment as well, right? Now the reason is, yes, you can charge more, but the thing at the same time, you will discourage John to answer the call, right? Because if you know when the cost of answering a call, even if both the caller and the caller party is in Singapore, you will stop using the roaming service, right? So at the end, you may not earn more. Just like let's say you use a mainland GSM phone, you travel to Hong Kong, right? If you know that there is no special arrangement for you, if you call your friend in Hong Kong or your friend call your number in Hong Kong, when both the caller and the caller party are both physically in Hong Kong, you still need to pay for international charge, right? Then that will discourage you from using the roaming services, right? So therefore, the motivation of the operators is to reduce this scenario so that especially the mobile operator has the motivation. Because this international charges is not paid to the mobile operator, it's paid to the international carrier. So as a mobile operator, you want to do something about this so that you encourage your roamers to use your mobile services when both the caller and the caller party is in the same area. Okay, so that's the background. Okay, so you notice that in solution 1 is trying to basically modify the international switching carrier. Now, if you look at the procedure, in both the registration procedure and the call setup procedure, the international switching center has to deviate from the standard practice. Okay, so yes, theoretically speaking, this way is a solution. Now, the nice thing about this solution is this arrangement is transparent to the caller. Jenny doesn't need to know there is such an arrangement. Jenny just called John's number in the same way as before. Okay, but then the network itself will automatically bypass the unnecessary international segment. Okay, so that would be the ideal scenario for the user perspective. But in the business arrangement, this is not that feasible because, as I said, the motivation is the mobile operator in Singapore's network, right? There is not much motivation for Singapore's international switching carrier to do this modification. So this is not a standard practice So you require cooperation of the International Switching Center, which is a different company, to modify the protocol to adopt this solution. Okay? Unless the mobile operator and the international switching carrier are the same company or same holdings. Otherwise, they won't have the motivation to modify the protocols to facilitate this kind of roaming, reduced roaming charge. Okay, so that's the disadvantage of solution one. You require modification of international switching carrier, which is usually not the same company as the mobile operator. So therefore, you have a solution two. Whoever has the motivation should adopt the modification. Okay, so you still essentially keep the roamer location cache approach, but now the roamer location cache is within the mobile operator. Okay, so therefore, this is the standard international switching carrier. So in the registration procedure, you go through the same idea. Whenever there's a database transaction between this visiting location register and the home location register in Taiwan, this roamer location cache will keep a copy. So this will act as a proxy for the home location register. All right? Now, during call processing, when Jenny calls a number, now in this case, Jenny cannot call John's regular number, because if Jenny calls John's regular number, the call will go to the PSTN, and PSTN look at this number is the Taiwan international number. Then the trunk will go to the international switching carrier. Once the trunk call setup goes to the international switching carrier, and this is a standard international switching carrier without modification, then the call will go to the Taiwan ISC, etc. And then it will be too late to reverse it because SS7 is not reversible. Is that okay? So, therefore, in order for this to work, since only modification is the local operator, mobile operator, roamer location cache is with this mobile operator. So in order for this to work, when Jenny called John's number, Jenny has to be aware that John is in a roaming stay in Singapore. Jenny will first have to call a special access number specific to this operator. So when after he called this access number, he has to key in the username, password, or whatever. And then after successful authentication, then this you will be asked by the local operator to key in an encapsulated number, the number you want to call. So this becomes a proprietary calling arrangement. Jenny has to call a different number in order to enjoy this service. Is that okay? And that is an attractive arrangement overall, because if you travel to Hong Kong, sometimes, I don't know about nowadays, but in those days, if you travel to Hong Kong, if you take the airport express, you actually, there will be some small card distributed to you, saying that there are some reduced roaming services, and basically it's using this kind of services. If you want to make use of this reduced roaming arrangement, you need to call a special number before you call your friend in Hong Kong, right? So, yeah, so this is the arrangement. Now, but then the disadvantage of solution 2 is for the mobile operator, yes, you have the motivation and therefore you do the modification. But you still need to modify the standard switch, and you need to modify the handshaking of visiting location register, okay? Because this is not the standard arrangement. The standard arrangement doesn't have this roamer location cache. Visiting location register will only update the home location register this way. Okay, it will not go through the RLC. Okay, so you need to modify the visiting location register in order to adopt this roamer location cache. Now, solution 3 is trying to reduce the modification. It's still modification within the operator, but now in addition, instead of modifying the standard protocol of VLR, you just install the roamer location cache arrangement as an add-on. So you just have a sniffer extractor to extract the handshaking between visiting location register and home location register. So this visiting location register will do handshaking in the same standard way, okay? So without any modification. It's just this sniffer, it's this extractor that extract a copy and create a proxy locally at the mobile switching, at the local mobile operator in Singapore. Okay. Now in this way, Jenny still has to call a special access number to enjoy these services. Okay. But the modification is entirely within the mobile operator and doesn't require modifying the standard elements. Okay. So it's just an add-on to enjoy these services. Is that okay? So the idea of these 3 solutions is to avoid the call being routed to the international switching center if you are not able to modify this guy. Okay? Any questions? Okay, if not, let's take a 10 minutes break. And then after that, we'll come back to talk about the corresponding core network services for the packet switch domain. And then that will be the entire scope. Okay, so let's take a 10 minutes break. Testing. Okay, let's resume. So let's focus on this final part of the core network access for internet access for the packet switch domain. Okay. So now we have, before the break, we have explained the traditional 2G core network services. In particular, we talk about mobility management, and we also talk about call control. That is how to make outgoing call requests and incoming call requests, so-called call termination. And why we need the mobility management, we need to know where is the location of a user to support call termination. All right? And now let's look at what about 3G, what about packet switch domain. Now, in order to explain or to appreciate the convenience of 3G packet switch core network services, we need to first understand how 2G provide internet connection. In fact, for 2G, namely GSM or IS-95, it can also support internet access. Okay? We briefly talk about this when we talk about call processing, but this is an end-to-end picture once again. So remember at that time, for 2G, this is around 90s. In 90s, if you want to access internet at home, it's not like today. Today you plug into the Ethernet interface and you automatically have an IP-ready Ethernet connection, 24 hours. But in those days, it's not. In those days at home, if you want to access the internet, you subscribe to an internet service provider. The internet service provider will just give you a dial-up number. They call this dial-up ISP. Let's say the number is 1, 2, 3, 4, 5, 6, 7, 8. Okay. So the end-to-end architecture is like this. This is PSTN. This is the ISP, Internet Service Provider, which consists of a bunch of V.90 modem pool. At home, you have a laptop, and laptop has a V.90 modem. Let's say this is your COM1 device. If you want to make an internet call, if you want to access internet, browse the internet, you first need to command this V.90 modem to make an outgoing call request. Call this number. When you make an outgoing call request, it will basically initiate a telephone call to the PSTN. The PSTN receiving this called number will know that it will set up the trunk accordingly to this destination number, to this called number. So by the time that this ISP modem answers the call, this V.90 modem will handshake with this V.90 modem, right? You will hear some kind of signaling noise. And during this V.90 modem handshaking, after the handshaking is done, the two sides establish a V.90 layer 1 connection. So the layer 1 connection is end-to-end. And based on that, the laptop layer 2 protocol called PPP will handshake with the PPP protocol in the ISP. This is usually for authentication and also distribution of IP addresses. And after that, you have an activated IP address. And then this is IP. Through this IP, you connect to the internet. And somewhere in the internet, you have a web server. Let's say this is HTTP server. So on this HTTP server, on the laptop, the next layer is TCP. So the TCP will set up a socket with the TCP layer in the web server. Based on this end-to-end socket, you run the application, let's say HTTP, and HTTP here. So that's the end-to-end protocol flows when you want to access internet, browse the internet at home at that time, okay? So that's why this is called dial ISP. The entire connection is circuit switch based. At that time, you have to pay for airtime. So if you browse the internet for 1 hour, you pay for 1 hour of charge, okay? So at that time, I said that the 2G network, GSM or IS-95 mobile network, they also support browsing internet when you're outside, okay? So when you're outside, you are still connected to the same ISP, Internet Service Provider. So the Internet Service Provider does not need to be aware you are inside or outside, okay? So, but when you are outside, you carry the laptop outside, and then now you have a mobile phone. Let's say this is a GSM mobile or IS-95 mobile. At that time, there is an infrared connection, IR port, infrared port, which is like today's Bluetooth. You can think of it this way. So through the infrared connection, let's say your mobile device appears as a COM device. Let's say this is COM2. You still have the V.90 modem as COM1. Okay, but that mobile device is connected through your COM2. So in this way, in this case, when you want to browse the internet outside, making use of a 2G mobile network, you will have to use a COM2 interface to ask this mobile to dial the same ISP number, 1, 2, 3, 4, 5, 6, 7, 8. So this connection will go through the, let's say, GSM network, okay, as a whole. And GSM network, look at this number, know that this is a fixed line number. So the trunk will be set up to the PSTN, okay? And then the PSTN will, receiving this coded number, will know that this is the destination number. So we'll continue to set up the trunk to this Internet Service Provider. The problem, as we talked about a while ago, is when Internet Service Provider answers this call, this V.90 modem will start handshaking, expecting there is an upstream V.90 modem to do handshaking with it. But if you look at this entire flow, nobody in the upstream will speak V.90. Not this one. Although you have a V.90 modem, but you are not using that. Remember, you are using COM2. You bypass COM1 for this connection. Okay? So if you just do this connection like this, then you won't be able to support Internet Service Provider connection. So to get away from this problem, remember in Chapter 2 we talk about the GSM mobile or IS-95 mobile have an arrangement So instead of terminating your call to any arbitrary node, it will terminate your call to a interworking function, IWF. This interworking function is a physical layer gateway. So it translates between V.90 and, let's say, GSM proprietary. Okay? So the whole setup remains to be the same, but then when ISP answers the call, this V.90 modem will do handshaking with the V.90 modem at the interworking function. So these two guys will do the handshaking and set up a layer 1 connection, but that layer 1 connection is not end-to-end. The interworking function will have another layer 1 connection through the GSM protocol, okay, with the handset and eventually the laptop. Okay? So the entire end-to-end layer 1 connection consists of 3 segments. The first segment is infrared connection between the laptop and the mobile. The second segment is GSM between the mobile and the interworking function. The third layer, third segment is V.90 modem, V.90 layer 1 between the interworking function and the internet service provider. So the entire layer 1 is partitioned into 3 segments. Okay? But to the internet service provider, this design is supposed to be transparent to the internet service provider so that the internet service provider doesn't need to be alert that you are outside or inside. It will answer the call in the same way. So therefore, in this case, in the 2G methodology of providing internet access, the role of the GSM network or mobile cellular network is just to provide a layer 1 connection. And this layer 1 connection is not even end-to-end. And that's it. The end user has to take care of all the other protocols. For example, after you have this fragmented layer 1 established, the next protocol is a PPP. PPP protocol is transparent to the GSM network. It's not within the GSM network. This PPP protocol, in the same way as when you are making a connection at home, terminate with the PPP connection at the internet service provider for username and authentication, and then distribution of IP address. These 3 major functions. After that, you have IP with the activated public address, and then IP here, and then you have TCP, setting up a socket, TCP socket with the web server in somewhere in the internet. And then based on that, you have HTTP with the HTTP application in the web server. Notice that all this layer 2 onwards protocol is not within the scope of GSM network. It's not within the scope of mobile network. So in other words, in 2G, the mobile network just gives you a cellular data bearer, a layer 1 connection. So this is a cellular mobile data. Cellular data bearer, a virtual layer 1 connection, and that's it. Subsequent protocols onwards, beyond the layer 1, is the responsibility of the end users. Okay? So that was a primitive method of providing internet access in 2G circuit switch domain core network. Now this arrangement has a lot of issues, I'll explain this in a minute after we talk about 3G. Now, so this is the 2G situation. 2G just gives you a cellular data bearer, virtual layer 1 connection. If you want to access the internet, you need to take care of the subsequent protocol required to get an IP address, to do this and that. Okay? The mobile network is not responsible. Now, but 3G, how is it different? For 3G, as we explained, when you set up a packet switch connection, that involves activating the signaling bearer and the data bearer, right? So you have a signaling plane and user plane. Both the user plane and the signaling plane are riding on top of this logical channel provided by RLC. And the logical channel will be mapped to transport channel through the MAC layer. Okay? So that would be the mobile devices, the protocol stack in the mobile devices. Now, then this is a serving RNC. The serving RNC will terminate up to RLC in the control plane, right? And then the data plane will terminate into SGSN and GGSN. So these are the, you can think of that as IP router, but with mobility management support. So these are essentially IP routers in the core network of the packet switch core network, in 3G network. But these are not ordinary IP routers. They are endowed with an additional function, mobility management, GMM. That means they keep track of the routing area, latest routing area of where this mobile device is. Okay? Now, when you set up, remember that when you get connected in part 2, we have 2 steps, right? Step 1 is to activate the control bearer or signaling bearer. Step 2 is to activate the data bearer. After you finish step 1 and step 2, you have an activated data bearer. This data bearer is IP ready. You already have the IP address distributed to you through this session management. This session management plays the same role as PPP. Okay? But this session management is a control plane protocol riding on top of GMM, GPRS mobility management. Okay? So through this session management, you activate the IP address. And once you activate the IP address, between the mobile and the infrastructure, the core network, the mobile, in this case, the 3G mobile network, provide you a logical data bearer. This data bearer is IP ready. So this is in big contrast with 2G. 2G, the mobile network, just provide you a bare bone layer 1 data bearer. No protocol structure at all. The end user has to figure out yourself how to get the IP address and the rest of the protocol structure. It's the responsibility of the end user. But in 3G, the mobile network, the 3G packet-rich data network, will provide you with an activated data bearer. And this data bearer, as I said, is a virtual connection. It's a virtual logical connection. IP ready. You already have an IP address. And also, all the handover, power control, radio-dependent functions, dynamic bearer control, they are all handled by the RRC. So if you are the application programmer, programming the app on the data plane, what you see is an IP-ready data bearer. There's virtually no difference for you to program an app in a 3G device versus program an app for the fixed line computer. In both cases, you can assume you have an IP-ready connection. Okay? So that's a big difference. So you understand what I mean, right? So the contrast. In 2G, you don't have the mobile network operator do not provide you an IP address. You figure out how you should get an IP address and maintain the IP address. You also need to figure out all this handover, whatever arrangement. But in 3G, everything is provided by the protocol stack control plane. Radio resource function is taken care by RRC. The dynamic bearer, the bursty traffic comes and goes, taken care by RRC. The IP address activation taken care by SM. The mobility management, routing app, knowledge of your location, taken care by GMM. Okay? In the data plane, what you have is a stable data bearer, IP ready. IP address is already activated when you are connected to the internet. Okay? So, in other words, in 2G, the mobile operator and internet service provider are 2 different parties. They are 2 different companies. They do not interfere with each other. As I said, mobile operator just give you this segment. ISP is somewhere in the PST and totally unrelated to the operator. Okay? But in 3G, the mobile operator and the ISP can be integrated together. Okay? And usually, and as of in practice, mobile operator will also own these public IP addresses and distribute the public IP addresses to you. So in other words, 3G mobile operator also act as the internet service provider. Okay? Now, this is the functional aspect, but there is also an associated performance aspect. Now, remember when I talk about previous chapter last time, I say that from time to time I come across, you have studied OSI 7 layers, right? So in your computer networking courses, you should remember you have physical layer, MAC layer, layer 2, layer 3, layer 4, blah, 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 right? Network layer, application layer, transport layer. So most students will, after studying computer network, will be able to comprehend this protocol stack on a vertical dimension, meaning that you expect layer 1 to do something, layer 2 to do something different, and each layer will do something differently, different from the other layers, right? So this is a partitioning of function, the modular design. But not many students also have the corresponding perspective of a horizontal peering concept. Now, if you only have vertical partitioning of functions without the horizontal peering, you only get half of the picture. Now, what do I mean by this? Now, just using this example, if this is using TCP/IP, this above the IP would be TCP. So you have TCP here. We know that if you studied TCP before, you know that if you lose a TCP packet, the TCP layer will be responsible for retransmitting the TCP packet, right? There is a retransmission window, right? RLC, as we talked about last time, also have a retransmission function, right? So if you lose an RLC packet, if you transmit an RLC packet to the serving RNC, you don't get an ACK, the retransmission buffer will initiate a retransmission of RLC packet, right? So now if you just from the vertical perspective, where you expect partitioning of function, you notice that there are two layers, RLC and TCP, having the same function of packet retransmission. You know what I mean? Is it a duplication of functions? Is the RLC and TCP duplicating the retransmission function? If yes, then does that mean we can remove one from the others? The answer is no. Although they both take care of retransmission, they do not have duplication of functions. The reason is because this is the horizontal peering concept. The TCP layer is end-to-end. If you look at this picture, the TCP socket is between the handset and all the way to the web server. It's transparent to all the base station controller, core network, even the routers in the internet. But RLC, the peer is between the scope of the RLC is between the mobile and the serving RNC. So these two layers have different scope. The retransmission mechanism is also different. Now, in order to explain why it seems to have two layers doing the same retransmission, but they still must coexist. It's not a duplication of function. We need to explore. First of all, if you look at TCP layer in a fixed line internet, this is a server. So when TCP is designed or invented, it's for fixed line internet. Okay. So when TCP layer send a packet, why the TCP packet will be lost? If you send a IP packet with a TCP as a payload, why the other side may not receive a TCP packet? So that you need to build in a retransmission mechanism here. What is the reason when TCP send a packet, the other side, the other TCP may not receive the TCP packet? So that you need to prepare for retransmission. Why? So this is going through the internet, right? First of all, it's a fixed line network. So for each communication link with a fixed line, the bit error rate is actually pretty low. The bit error rate we are talking about for a fixed line, let's say this is a T1 connection or whatever. In the old days, every T1 has a bit error rate requirement. So I forgot the order. It's something around bit error rate of around 10 to the power minus 9 to 10 to the power minus 12. This kind of order. So that means most of the time you won't have any bit errors or transmission errors. So the fact that the TCP packet do not get to the other side will not be due to, very likely, will not be due to transmission error, right? It's not. If this is a radio interface, the bit error rate we are talking about, as we talked about in last chapter, is of the order of 1% to 0.1%, okay? So different order of magnitude difference. So in a wireless network, when you send a packet across the radio interface, it could be due to bit errors, transmission errors. But for fixed line network, this is very unlikely, right? Still, given that this is not, all the links, we can assume all the links are very reliable. Very rarely you have transmission errors. Still, why the other side may not receive a TCP packet? So that you need to prepare for retransmission. You understand what I mean? If the transmission link are very reliable, then why when you design the TCP protocol here, why you need to prepare for retransmission? You need to prepare for retransmission because there will be some non-negligible chance that the other side may not receive the TCP packet, right? Why? Let's look at what is Internet. In the Internet, in a nutshell, it's a bunch of routers interconnected with each other, right? What is a router? What is inside a router? So Internet is a packet switching network, right? So the first principle of packet switching is what? Store and forward. Every router operates using a store and forward manner. Before you know where to forward the packet to the next hop, you need to first store the packet. You store the packet and then you look at the IP address, destination IP address, before you know where to deliver the packet. Okay? So every router has a switching fabric. The switching fabric will provide flexible interconnection between certain input port to certain output port, right? So there's a switching fabric. Since it is a store and forward, so that means you also have, so this is the first element. The second element is you need to have a buffer. Without a buffer, how do you store, right? You need to store the incoming packet before you know where to deliver to the output port, right? So that buffer is the second element. The third thing is, of course, you need a control. You need to process the IP header, and based on the IP header, you extract the IP destination address, and then you look up the routing table, etc., to determine where to forward the IP packet to the next hop, right? There's a hop-by-hop processing this way. The keyword is store and forward. Now with this store and forward, let's go back to the question I asked you. So why the other side may not expect a TCP packet? Why the transmitter sends a TCP packet, the other side may not receive it, given that all the links are very reliable? The issue is due to congestion. What is the congestion? For example, if this router has a lot of incoming traffic, there are a lot of incoming IP packets going to this router, then what happens? This input buffer may be full, right? If this is a router here, and the input buffer is full, and there is an incoming IP packet coming in, what happened? What can you do? You're the router. There's nothing you can do. You can only drop this packet, right? Because you must do store and forward processing. You need to first store the incoming IP packet into your buffer, and then you process it one by one. Now, if your input buffer is full, you have no places to store the incoming packet. The only thing you can do, the only option is you have to drop it. That's why when you transmit a TCP packet to this router, if this is experiencing congestion due to buffer overflow, this packet may be dropped. If it is dropped, it will never appear on the receiving end, right? So if it never appears on the receiving end, that's why you need the TCP layer to take care of retransmission business. Is that okay? In fact, if the other TCP layer systematically lose a packet, it will assume it will not just retransmit. This is called congestion control. Congestion control has two actions. First, we transmit the TCP packet. But since if the root cause of losing a TCP packet is due to congestion, right? You assume this node is congested. If you keep on retransmitting, would that help? You know that the upstream highway is congested. You keep on sending loading to this congested route. At the end, what happened? At the end, nobody can get through, right? So, in addition to retransmitting the TCP packet, you will also trigger a windowing mechanism. So, if you studied TCP before, there is a window. So in response to congestion condition, you will also shrink the window. If you shrink the window, the TCP source will be more humble to send out data. Okay? If you have a small TCP window, you will not be that aggressive to send out the TCP packet. You will be more humble. Okay? So that means you will reduce the loading to the upstream routers. If everybody behave in a humble manner in response to a congestion condition, then this congestion condition can get relief, and then at the end you will pass through the packet again. So that's called congestion control. So remember, the action is not just retransmission, but also shrink the window. Okay, so that is a built-in congestion control mechanism within TCP. So all the legacy TCP layer, whenever you lose a TCP packet, you will assume this is still the congestion. Okay, and then you will naturally trigger the congestion control mechanism. You shrink yourself with a smaller window so that you will be more humble to send out packet. Okay. Now, if the condition of the congestion get relief, you will expand your window gradually. So there are some detailed protocol on the TCP window adjustment. Okay. Now, this is so far so good for fixed line internet, but the problem is, now let's say in the 3G. In the 3G, we were talking about, okay, why we have a TCP doing retransmission at the same time we have RLC doing retransmission. Let's say we remove the RLC. If we remove the RLC, seeing that TCP layer already take care of retransmission, why do I need to take care of retransmission again in the lower layer? Now, if I remove the RLC, what will happen? If I remove the RLC, don't forget this is a radio interface. The radio interface has a bit error rate of around 10 to the power minus 3, okay? Which is order of magnitude higher than the fixed line bit error rate. So if you go through, send a TCP packet across a radio interface, it could happen that the packet cannot get to the other side due to transmission error on the radio interface, right? Now, if this is the case, but these are the legacy TCP layer that are designed for fixed line internet. Now, this TCP layer will always think if I lose a TCP packet, it must be due to congestion, right? But in this case, it could happen that the internet has no congestion, but you still keep on losing the TCP packet because of the transmission error over the radio interface. You understand my point? Now, if that's the case, the TCP layer, the legacy TCP layer, will always assume this is still the congestion. In response to that, it will always trigger the congestion control mechanism, retransmitting the packet, at the same time shrink the window, shrink the retransmission window. Now, if this is due to normal congestion, when you shrink the retransmission window, the congestion condition will get relief, and then you will gradually be able to expand the window. But in this case, this is not due to congestion, but you think this is due to congestion, so there is a mismatch in the reason. So after you shrink the retransmission window, the systematic packet loss still occur in the radio interface because this is due to transmission error. It's not due to congestion. So the TCP layer will keep on shrinking the transmission window until the transmission window becomes very small. That means you are very humble. It is very difficult for you to send a TCP packet because of this restricted windowing, right? So in this way, you will forcibly trigger the built-in congestion control mechanism. And by triggering this congestion control mechanism for the wrong reason, the only end game is your congestion window will be, your retransmission window will be very small. When your retransmission window becomes very small, your source rate will be very, very limited, despite there is no congestion in the internet. Is that okay? So that's why this layer cannot be eliminated. This layer provides a reliable logical connection between the UE and the serving RNC across the radio interface, right? So therefore, with this RLC retransmission protection, the TCP will see a reliable logical connection or reliable data bearer. So because of the protection from RLC, the TCP packet, whenever it loses a TCP packet, it must be due to congestion in the internet. So that's why you see that the scope of protection is different. RLC retransmission just provide a protection across the radio interface. The goal is to provide a reliable data bearer between UE and the serving RNC. TCP retransmission, the scope is end-to-end. The TCP retransmission is to protect against congestion. So these two layers are doing something else, a different thing, because of the different scope. RLC retransmission is to protect against transmission error. TCP retransmission is to protect against congestion problem in the internet. Okay? So as a result, both layers should exist at the same time. And in fact, thanks to this RLC, the TCP layer terminating across the mobile device will not have any major issue compared to TCP operation in a fixed line computer. Is that okay? So although both have retransmission, but we should not be that superficial. We have to worry about or be mindful about what's the scope of protection, because the retransmission is after different causes. Okay? Now, back to 2G. What's the problem? For 2G, you see that the cellular operator provides just a layer 1 data bearer. There is no protection at all. There is no protocol provisioning at all. You take care of the IP address activation in the control plane. But what about the data plane? For the data plane, there is also no protection against, this is across the radio interface. So this layer 1 connection provided by the cellular data bearer is not reliable. It's also error prone. And now you terminate the TCP directly all over the radio interface. So if you do it this way in the 2G network, you will suffer from all the time falsely trigger congestion control, as I explained. Okay? Because now to the TCP, it will see an unreliable connection across the radio interface. Okay? But TCP will always assume any packet loss will be due to congestion. So in this way, every time a TCP loss a packet, it will trigger the congestion control mechanism, shrink the window by half. And after shrinking the window by half, it will still have experienced TCP packet loss because this is not due to congestion. And then you will keep on exponentially decreasing the TCP window until you reach the minimum window. So in this case, the TCP source, if you terminate TCP across the radio interface, the TCP source becomes very humble. You are sending very low bit rate to the connection. So your performance, TCP throughput, will be very poor in this case. Is that okay? Now, so therefore, in 2G, before we have 3G at that time, there was an interim solution to this. The interim solution is we should not terminate the TCP across the radio interface. So then in this case, how do we access the web, how do we browse the web? Because all these web servers exist in the internet, they expect TCP, because those are legacy TCP layers. In every web server, they have TCP layer. So before you can start the HTTP, you must have a TCP socket, right? So where do you terminate the TCP socket? So that is the so-called WAP solution, WAP solution. So that was very popular around year 2000, before we have 3G. So with WAP, the idea is you introduce a WAP proxy or WAP gateway. So this is the radio interface. This is a WAP phone, WAP device. So between the device and the gateway over the radio interface, you are not using standard TCP. You have a proprietary protocol called the WAP protocol. This proprietary protocol will not have this kind of congestion control mechanism anymore. But on the web server side, the web server expects TCP termination. So the TCP socket will be between the web server and the WAP proxy. Okay? So the socket is not end-to-end. It's only between the server and the proxy. And then from the proxy, you will have another transport layer connection, which is proprietary to the WAP protocol stack. So in this way, you avoid terminating the TCP over the radio interface. And then you avoid falsely triggering the congestion control mechanism. Is that okay? So that was the solution. But this solution, so this is a proprietary protocol. So this is a transport layer. UDP is the same as the standard UDP, but the TCP is replaced by WDP. So this WDP is proprietary to the WAP protocol. So this WDP will not have this falsely trigger congestion control mechanism anymore. Okay? Now, but while you think that this is a solution, now for regular web browsing, this is fine. You just have a proxy that when you want to browse a web page, the HTTP request will go through the proprietary protocol to the web proxy, and then web proxy will re-encode your request with a standard HTTP request. This HTTP request will go through the standard TCP socket between the gateway and the web server across the internet. And then this web server will respond with this WML content and go through the TCP socket to the web gateway. Then the web gateway will re-encode the standard HTTP response with a encoded HTTP response. So this part is proprietary. Okay? So in this way, you will be able to display the content through the help of the web proxy or web gateway. Is that okay? So that was the arrangement. A gateway or proxy always act as a protocol translator. You translate between two different languages. Think of it this way. Okay? However, for regular web browsing, this is fine. But if you are serious about some application with security concern, then this is far from okay. Now, at that time, that was around year 2000. So in Hong Kong, the Hong Kong government rolled out something called MPF, Mandatory Provident Fund. So it's a compulsory saving scheme for your retirement. So it's a big market at that time. There are quite a lot of these financial institutions offering these MPF services. So they want to compete for customers. So at that time, they want to, now of course now it's more like internet banking. Now it's everywhere. But at that time, they want to, it's before we have 3G. At that time, they want to use the web architecture to provide something similar to internet banking. So the customer will be able to browse and update the investment portfolio through the web devices. Okay? So at that time, but of course for this kind of application, the security is a big concern, right? So I was helping the company to do a security audit at that time. So using the web gateway solution, what would be the security risk? Now, first of all, the web gateway may be owned by the mobile operator like this. Okay, so, and then the financial company may have the customer data, customer portfolio, investment portfolio information is in the web server. Okay, now to provide one layer of security, the web server is isolated from the public internet through a firewall. Okay, so when the web devices of your subscriber want to access your own investment portfolio in the company, the connection will be through two separate segments. So you want to do like HTTPS, right? S stands for secure HTTP. And HTTPS means you have HTTP on top of this encryption layer, SSL, TLS. And that is on top of a TCP socket. But as I said, right, for performance consideration, in 2G network, you cannot just afford to terminate the TCP across the radio interface to the mobile device. And because of that, you use a web gateway or web proxy. So the layer 4 connection is not end-to-end. The TCP connection is not end-to-end. It's two segments between the server and the gateway, and from the gateway to the client device. Two segments, okay? Now, what would be the security concern in this case? So the two segments, also, if you look at the web protocol, there is also an equivalent security layer, WTLS and WTP. So you will have a standard encryption layer, SSL, TSL, over a TCP socket. You also have a corresponding security layer within the radio interface, within the web protocol stack. So in this case, what would be the security concern? Now you imagine you are the hacker. You are hiding somewhere in the internet. Do you see any opportunity of hacking into the data? Now assume you cannot do brute force hacking. If you can do brute force hacking, there is nothing is secure. That means you cannot get an SSL encrypted packet and brute force decipher this. That is not feasible, let's say. Okay? But still, with this arrangement, do you see any opportunity for hacking into the system, for hacking into the customer data? Again, assume the firewall is reliable. Okay? So you cannot hack through the firewall. Now the issue is here. Here in the web gateway, what happened? The SSL, the standard encryption layer, will have to run between two end segments of the TCP socket. Now the TCP socket is not end-to-end. So that means what? The encrypted data from the server, company server, has to go into the TCP socket at the web gateway. And then at the wrap gateway, you have to decrypt this and re-encrypt this with another encryption layer, right? So that means there will be somewhere in the wrap gateway, there will be a decrypted data available here because you have to decrypt this and re-encrypt with a new protocol. Is that okay? So this will be the security witness because you have to decrypt this from the standard SSL and re-encrypt this with the WTSL. These are two different encryption layers. Okay? So, and this web gateway is exposed to the public internet. So if you're hiding somewhere in the internet, you can just attack this web gateway. And then there will be some decrypted data here. And then you will be able to get this sensitive data without brute force decrypting the SSL or WTSL. Okay? So this is a major security threat. And then, so how do you deal with this? Now this is so fundamental, you cannot do anything about this because the TCP socket is not end-to-end. That's the fundamental limitation. Now you can only mitigate this effect. Now for example, okay, so since this also contains sensitive data. Now this is operator-owned. Now operator-owned means if you are the financial institute, you won't be able to even monitor for potential hacking because this is not your gateway. Okay, so what about you have a corporate-owned web gateway? Now with corporate-owned web gateway, the security witness still exists here. You have to decrypt and re-encrypt. But the better thing is this is managed by the company. And therefore, you will be able to at least realize there is any hacking attempt here by looking at the log or keeping at the log. Now, this is also exposed to the internet. So the next, the next solution may be, how about I put this web gateway behind the firewall? Now, if I put this web gateway behind the firewall, and firewall, you can think of that at this stage as like an IP filter. Allow some IP address to pass through and block some other IP address from passing through. If that's the case, okay, putting it behind the firewall, assuming this firewall is secure, okay, then you will isolate this sensitive data from the internet, right? However, this arrangement is also not feasible because this is the firewall is an IP address filter. So how do you configure the firewall? Because your subscriber may not be coming from one single operator. Your subscriber may be coming from multiple operators. So the IP address would be something that you cannot control. So therefore, it is very difficult for you to configure the firewall this way. Okay. So therefore, these three solutions cannot will have its shortcomings. And the fundamental issue, once again, is because you are not able to terminate TCP socket end-to-end, okay, due to this falsely triggered congestion control problem. So therefore, of course, this becomes history because once you have 3G, and now you can appreciate the beauty of 3G because of this RLC layer protocol. It provides reliable logical connection or logical channel between the UE and the serving RNC. So despite the physical layer is unreliable, the logical layer or the radio barrier seen by the TCP layer becomes reliable. So to the TCP layer, there is no difference than a fixed line connection. Okay? So because of that, when TCP loses a packet, it is due to a congestion problem. So there is no more falsely triggered congestion control. So with this 3G arrangement, a full protocol stack data barrier configuration, you are allowed to terminate TCP directly on a mobile device. So that means you are able to do HTTPS end-to-end. With HTTPS being end-to-end, there will be no security weakness as we talk about like this. Okay? There won't be any gateway to do decryption and re-encryption because now the SSL and TLS can go all the way to the TCP socket at your mobile device. Is that okay? So this is what I just talked about. If you terminate TCP directly on the client device without providing resolution for the transmission error, you will have systematically falsely triggered congestion control. Okay, so that would be the 2G network. But when we introduce 2.5G or 3G systems, due to this full stack arrangement, you will no longer have this issue because you can terminate TCP. You have the luxury to terminate TCP directly onto the client device. So to the application programmer, you virtually see no difference between programming a TCP at a socket programming for fixed line computer versus socket programming for mobile apps. So both basically virtually natively the same. And this virtually natively the same is not something you can take it for granted. It's due to the coordinated effort of all these protocol stacks in the control plane that enable such a stable, IP-ready, and reliable data bearer provisioning. So this will ease the job of application programmer. So this is a big contrast. Without this arrangement, if you are doing a 2G app programming, the app programming will have heavy burden on handling this radio resource related issues. Whereas in 3G, the app programming will be, so all these complication related radio resource related issues are shielded from the application programmer. So the application programmer just need to assume you have the same logical connection, IP ready, reliable, as if you are doing programming for the fixed line desktop computer. So that's why today you can have internet banking, you take it for granted. You take it for granted because you have HTTP, you have end-to-end secure connection. Because without that, you won't be able to do secure internet banking as well. Okay, so with this, I guess that's all I want to talk about, and that's all the examination would be. So the examination scope, of course, will only be restricted to the topics I cover in class. Okay, so those I skipped, those I didn't mention it, will not be examined. Is that okay? So in short, it will cover everything from Chapter 1. Chapter 2, which we only talk about circuit switch, IS-95, circuit switch connection, how to set up a circuit switch connection, what do we call it? Power control, soft handover, right? That's the circuit switch domain. And then for packet switch domain, we mainly talk about how to set up a packet switch connection and a dynamic bearer control. That will be the major thing in Chapter 2, okay? And for Chapter 3, obviously, it's about the core network services. In circuit switch domain, we talk about mobility management. And we talk about the core processing in an end-to-end perspective. So how do we support core origination requests? How do we support core termination requests and the associated application, roaming, international roaming? That's for circuit switch. And for packet switch, we essentially talk about the end-to-end picture. How the operator or how the core network provide end-to-end, how the core network for packet switch systems provide end-to-end internet connection. And then we compare with the 2G circuit switch internet connection versus the 3G packet switch internet connection and the associated implication. Is that okay? So that will be pretty much the scope. Now, any questions? So those I haven't talked about. Pretty much in Chapter 2, the evolution stuff, the post-3G stuff that I skipped will be outside the scope. Okay. Now for the examination, I fixed the examination paper already. It's in the process of printing. So what can I tell you? First of all, there are 2 sessions. So the session A will consist of multiple choice, true and false, which account for 60%. 60%. So that means that has several implications. First of all, with multiple choice and true and false, this is very similar to assignment 2, by the way. Okay. With this multiple choice and true and false type questions, I will have a block coverage, right? So it is not that easy to just focus on 1 or 2 topics. So that is for this purpose, right? You have a broad coverage on many concepts and details. That's number 1 implication. Number 2 implication is I believe in probability, right? So with this multiple choice and true and false, even if you flip a coin, you won't get. It is very difficult to get 0. Put it this way. Even if you randomly flip a coin or roll a dice or whatever. So you are allowed to bring a dice if that makes you feel better, but you won't be able to get 0 that easily. Okay. If you can get 0, probably you can also get a very high score. Depends on what you want. So that's session 1. Section B will be a bunch of long questions. I forgot how many questions, but similar to assignment 1, that kind of, but as I said, right, those long questions will be divided into multiple parts. There will be, now if there will be any calculation involved, as I promised you, you only need to exercise addition, subtraction, multiplication, division. Okay, I won't ask you for doing any integration. I won't even ask you to do Fourier transform. So don't worry about those mechanical calculations. If I may not even ask you to calculate anything. What I mean is, if I have to ask you to calculate something, it will be just restricted to this 4 basic operation. Okay. But mostly, I will set up the long questions in the form of some case studies. So as I told you at the beginning, I will give you a certain situation. Maybe a situation will have some, I don't know, randomly, I don't mean I will do it this way, but just randomly. Well, basically, it's just like the kind of question I'm keep on asking myself, right, during the lecture. Although I feel like talking to myself most of the time. But these are the type of questions that I can ask you. I can break down a situation. For example, a mobile going through this particular trajectory, experience a certain core drop, for example. Now, I can randomly create a scenario like this, and then I can ask you to explain why. What do you think is the reason for core drop? Right? You can elaborate the potential reason you can think of, and there are no more model answer. Any correct answer will score full marks. Okay, so you don't need to guess what would be my model answer. Okay, if you are able to give a reasonable answer that I couldn't think of initially, right? So you will also get full mark if this is reasonable. Okay, so there is no model answer. So you can explain what, in your opinion, why the core drop or a certain phenomena. And then after I ask you to explain, and then the second part obviously will ask you to provide solution, right? So what do you think is a solution that can help the situation? You know, so those long questions will be of this kind of nature, okay? So that's why I don't think there's anything you need to prepare, because you either know it or you don't know it. So what I can guarantee is, as I just said, it sounds like bullshit, but you will be given 3 hours, okay? Just like the lecture time, 3 hours. So what I can guarantee is you will have more than sufficient time to answer the questions, okay? So if you cannot answer a question, it's not due to insufficient time, okay? So, and I will try my best to set up the question so that at the end the score will follow some distribution, meaning that it won't be too easy. If it's too easy, that means you may lose a grade simply because of some careless mistake. That is not a good way, right? And moreover, if I set up the question too easy, I feel it's like insulting your intelligence. That is probably not something I want to do, okay, either. So, but of course, I won't set up the question so difficult that everybody will be clustered at the low end of the spectrum. That is also not my intention. So hopefully, with this arrangement of multiple choice and long questions, we will see a healthy thread, okay? So from the experience over many years, what I can tell you is it is very difficult to get a fail, okay? Very difficult. You have to try very hard to get a fail. Of course, it's also not trivial to get a distinction, okay? So most will, if you fall into the middle ground, you will get what you deserve, okay? And don't forget, you are allowed to bring an A4 size cheat sheet, double-sided, handwritten. There is no constraint on how small you can write, so by all means, write as small as possible if that makes you feel better, okay? You can bring a calculator, of course, basic pens, pencil, whatever. Now I will leave sufficient space in the question paper, so you put all your answer directly on the question paper, okay? And at the end, you submit the entire question paper together with your answer. Now, if you find that the space is not sufficient, you can raise your hand and ask for additional paper. Okay, so you can ask for whatever paper how many sheets of paper you need. But if you find yourself in a situation that you need to ask for many papers, additional sheets, then be mindful that is not a good sign, because sometimes I see if I ask you something. Sometimes from previous years, I have some students who would basically how do I put this? It's like a core dump, okay? It's like a core dump. It's like I ask you something, and you basically do not know what I'm asking. You do not know the answer, but you try your best to put down everything related to the keywords, okay? Hopefully, part of that will hit. Now, that is a very bad way, and that is an obvious way to tell me you don't know what you are talking about, okay? And don't try to give me a core dump, okay? What else? Yeah, that's pretty much I can think of. And, well, any questions? Okay, so I can see or I can feel some of you looks quite anxious. So the only thing I can tell you is just relax. After the examination, you will feel that it's just not as difficult as you think. So I'm just bluffing you in most of this elaboration. And then, and most of the time, if you're especially in this chapter, you see a lot of terminology, jargons, whatever. So again, with this A4 size cheat sheet, I hope it will relieve you the burden from worrying about memorizing this and that. Plus, I won't be interested to ask you what's the definition of, for example, what's the definition of LC, what's the full name for MAC. So that is not my style, okay? So hopefully this will give you some peace of mind. Is that okay? You still look very worried. Anyway, what else? I forgot what I wanted to say. Okay, so that's what I wanted to say. No questions? Okay, very good. So I'll look forward to seeing you next week. And by the way, so please spare your 2 minutes to fill up the course evaluation in case you haven't done so. Deadline will be in this week. Okay? And thank you for your patience throughout the semester. So I hope I will still see smiling faces next week after you finish the examination. Well, at least I hope you will still talk to me when you come across me in the corridor after the examination. Okay, I'll see you next time.